Today's episode is brought to you by one of my favorite podcasts. It's called Everything Everywhere. It's one of the most popular podcasts in the world, and its host is one of the most interesting men you'll ever meet. Remember that TV commercial guy? The most interesting man in the world. Gary Arndt is that man in the real world. In 2007, he sold his house to travel around the world, and he's been everywhere, all 7 continents, almost over 200 countries and territories, all 50 United States, over 400 UNESCO World Heritage Sites. He had a triple major in college, mathematics, economics, and political science. He went bungee jumping in New Zealand, floated in the Dead Sea. Hey, I did that. That was pretty cool. Crossed the Arctic Circle in the Yukon. I didn't do that. Rode in a Formula One car at 180 miles an hour. I definitely didn't do that. Swam with whale sharks in Australia. He went spelunking in Borneo. Swam with jellyfish in Palau and many other adventures. So this is what makes the podcast Everything Everywhere so interesting. Each one of them is just maybe 10 to 15 minutes long, usually maybe 13, 14 minutes. And you can just queue up one every single day. Just could be on part of your commute or while you're vacuuming the house or walking the dog or whatever it is you're doing for 15 minutes. And then you can just vacuum up this really interesting content that he produces. Let me just give you some samples from the last few weeks. The history of money. Oh, we talked about that one. Sandwiches, aircraft carriers. Yeah, cool. King George III, Sergeant Alvin York from World War I, Ernst Shackleton and the rescue of the Endurance, the history of coffee. Wow. The Telemark raids. That was a World War II adventure. The kidnapping of Charlie Ross. Solar eclipses. That's appropriate because he did that right. The last solar eclipse we had. So check it out. The podcast is called Everything Everywhere. It's available on all your favorite podcast platforms. Check it out. Gary Arndt is the podcast host. Super interesting guy. Super interesting podcast. All right. Here's our show. So what's your story? Give us your life origin story. How did you get into all this?
Origin story, very small town in Austria, very close to Salzburg. So Mozart, classical music, lots of Alps. And I really didn't think I would be able to, work with NASA and big space missions trying to find life on other worlds. But there was this small conference when you were like a student. You can go to these small conferences. Sometimes there's a little bit of money. So you go. And they were talking about these new worlds that they had just found around other stars. And I was like, oh my God, that is so exciting. And I would love to be one of the explorers who helps find out what they are like. And that's how I got into it, even from a tiny town in a tiny country. And now I'm here at Cornell University in Carl Sagan's office, thinking about how we could spot life in the universe.
Were there any obstacles to being a woman in the physical sciences like we've read about from the bad old days, or was it pretty good by the time you got entered into the field?
I think I got really lucky because the first bosses I had were Swedish. And so they took a little bit more care of trying to make sure that I wouldn't do the coffee and the copies. So I was an engineer, right? So they were basically trying to work against the stereotype. And all the trailblazers before me, everybody who put their path made it so much easier for me. And I'm trying to do that too, because we do have ways to go. But I think everybody knows that, whoever you are, whatever gender you are, sometimes at work, there's something that's not fair, that doesn't work. And it's just good if somebody can help you out. But I think one advice I would have for young women, especially, whether it's in science or whether it's at work, is selective hearing. Get selective hearing as soon as possible, because a lot of people will tell you you can't do this. And if you can zoom them out somehow, that's a huge step forward.
So mentorship.
I think mentorship, absolutely. Pick somebody that you trust, or pick a few people that you trust. And then once you do that, listen to their opinion over many other people's opinions. I think especially when you're young, that helps a lot. After a lot of experience, you can basically say, "Ooh, this is kind of just somebody saying something, and this is somebody who really has like some opinion that you should count." But in the beginning, it's hard to judge. And so having mentors who help you put that in context, I think is really useful. And then sometimes try to do it with humor, right? Because, for example, when I get asked if I'm married, a kind of illegal question in most countries, I usually say, to my laptop. Who doesn't like a workaholic?
Wait, wait a minute. People ask if you're married. Who asks you that?
Oh, job interviews. Remember these illegal questions? And I'm like,
Wow.
well, one of the key things is like, I got the advice a while ago is like, if somebody asks you an illegal question, you under no obligation to tell the truth.
Yeah. Well, I mean, that's one of those questions from the bad old days when it was worried that you'd get married, then pregnant, and then you wouldn't be on the job. So we don't need to hire you now, right? I mean, that's why it's illegal to ask that.
Right.
Interesting. Okay. And speak to us
But I,
a little bit about
but
the.
I think
Oh, please go
for
ahead.
science, sorry, but I think for scientists, like being married to your laptop is actually not
I
a
see.
lie. We
I
usually
see.
are.
Yes. Yeah. 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 Of course. Yeah. It's one of those questions on a job interview. What are your flaws and weaknesses? I work too hard.
Exactly, exactly. And then you're just like, I don't know when to quit. I keep working for you the whole time.
Or dark chocolate. Oh, yeah. Okay. Right. Speak a little bit about the influence of Carl Sagan today. Still, we're coming up in a year and a half on the 30th anniversary of his death in 1996. You talk a lot about Carl in your new book, which I forgot to properly introduce. It's called Alien Earth: The New Science of Planet Hunting in the Cosmos. Of course, Carl was one of the pioneers of that whole science. Where you're in his office there, he died really before the internet even became a huge thing, and he has a massive digital presence. It's astonishing
Mhm.
for somebody that's been gone for so long.
I think Carl has this vision, right? He had this vision that he could share with everyone. And so I think that resonated throughout the world in his Cosmos series, but just his passion, his love for the subject, his love for bringing us closer to the cosmos and interweaving it also with humanity's history, with the strides we made, with the things that we figured out, and how curiosity basically helped in the olden days. And it does the same now. And I think this is timeless. And he also had this love for people. Whenever I listen to him, I have this feeling that he liked everyone, right? He wanted to bring everyone on board in this amazing discovery that's our journey through the cosmos, that's our journey to uncover the mysteries. And I founded the Carl Sagan Institute here at Cornell because he has been here and he laid the groundwork to connect different fields. So, for example, have people who study the earth, right? Have people who study stars, have chemistry, have biology. Because if we're trying to find life in the universe around planets that orbit other stars, we basically need everybody and everybody's ideas together. And so he started to establish this here at Cornell, and he died way too young. But standing on the shoulders of giants, by chance, at one point, we actually went around the room in the Carl Sagan Institute that has like a lot of people right now, from professors to the youngest undergrads. And we said, like, oh, did Carl have any influence on you? And everyone either read Cosmos or saw the Cosmos series or had some other connection. And it was kind of really surprising because, as you said, he has been gone for a long time, but his presence, his ideas are still interwoven, especially in the scientific life. And a lot of people became scientists and engineers because they heard him speak about the love, about the universe, and how we can make a difference and how we embed it in this gorgeous cosmos.
And how are you funded, and what kind of work does the Institute do specifically?
So specifically what we do is we trying to develop the toolbox to figure out if there's life on planets that are very far away around other stars. And for that, you need ideas from many different fields. How are we funded? Currently, we are funded by Cornell for a little bit, and then we're going to figure out how we're going to fund ourselves much further going into the future. But we have a lot of professors working on this, which are part of Cornell universities, but are really excited about this additional question about life in the universe. And so we brainstorm, we come up with new ideas, and then we put proposals into NASA, to the NSF, to other scientific private foundations and national foundations to get these ideas developed and to get these secrets unraveled.
Yeah, I remember E.O. Wilson telling me a story about meeting Carl in the 70s, and Carl was putting together some conference and then a book or proceedings. And he wanted Wilson, who is a biologist, to write something about the ecology on Mars. And he said, it's like, what? What ecology? What are you talking about? Well, I mean, think about it. What could you imagine it could be? And then go from there. It's like, oh, okay.
And I think this is where, exactly as you pointed out, he was just so visionary. He was like 10, 20, 30 years ahead of everybody else, and already was trying to envision what an ecology on Mars could be like, or how we could live there way before anybody else was even seeing a way to go there and do that. And I think this is why his voice is still echoing through our lives today.
Yeah, I sent you that essay I wrote, Measure of a Life. You can access it on skeptic.com.
It's beautiful.
I did a content analysis of all his writings and his work in the context of, is there a Carl Sagan effect? That is to say, if you popularize science, it hurts your actual conducting of science. Not true. He was amazingly productive as a scientist all through the production of Cosmos and the writing of his popular books and so on. He did not let up on the gas pedal of his original research in science. And I think that's also opened the door for people like yourself and other science popularizers who are actual scientists. You can do both.
Absolutely. I think you need to find somebody who can do both and who can show it like Carl Sagan did, because most of the time scientists are just curious by nature and they don't want to give that up. And doing both, finding a way to actually combine the passion to do the research, to figure out the secrets, but also get to talk about it and take everybody on board, because it is important, because we all live in this golden era of exploration. And lots of this funding is actually from, the National Science Foundation, from NASA, so from everyone. And so giving back a little bit by just showing what an exciting time we live in and what we're doing and what we're finding out, I think is very important to try to do both.
Yeah, I just posted on Twitter that his last interview on Charlie Rose, shortly before he died, warning about, basically talking about his last book, Demon Hunter World, about the dangers of having a populace that doesn't really understand science and technology, and yet has all this power. And, what a recipe for disaster that is. And that was before social media and all the divisiveness that's produced.
I have to say, this is my favorite. It's one of my favorite books. And I think it's as relevant now as it was when he wrote it. And that is kind of astonishing, because he basically asks all of us to just use critical thinking. And everybody can, right? But you have to have a certain amount of curiosity, and you have to give people a certain amount of facts and education to be able to use this. And I love his example with the dragon, in the garage. And I use this to teach my students scientific thinking by asking them to give me $50,000 for a dragon in my garage. And then they will use the scientific principles. They will ask if they can touch it, if somebody else has seen it, And so it's really important that that is something we don't lose, because you have to be informed to make a good decision.
Yeah, that's one of my favorite parts from that book. I call it Sagan's Dragon. I have a slide for it in my lectures on, imagine I have a dragon in my garage. Would you like to see it? Oh my God, yeah, that'd be so cool. All right, here it is. You open the garage door, person looks in, a couple paint cans, a ladder, a bicycle. There's no dragon. Where's the dragon? Well, you see, this is an invisible dragon. Oh, an invisible dragon. Well, how about this? We sprinkle some flour on the floor, and then we'll see the footprints of the invisible dragon as it walks around. Well, you see, this invisible dragon hovers above the ground a couple of feet. It's a levitating invisible dragon. Oh, a levitate. How about if we get one of those thermometers that we all use during COVID? You point and it detects the heat, and we can detect the outline of the body of the dragon from the heat. Well, no, this is a cold-blooded dragon. What about the fire that it breathes? It's cold fire. And then, of course, what's the difference between a cold fire, cold-blooded, invisible, levitating dragon and no dragon at all?
Dragon at all. As long as you can't tell the difference, right? And so what is so important in this example is that, at one point, you have to say there is no difference between it not existing or it existing, and you can tell. And so at that point, you have to make your own choice, whether you give me $50,000 for a dragon that you cannot perceive in my garage or not. Luckily, my students, when they walk out of class, don't. But it's kind of a really interesting exercise of trying to scrutinize when somebody tries to sell you snake oil. And so I think it's a good example. And hopefully, as you've done, they will remember the dragon in the garage and what to ask.
Now, that's easy to apply to things like the paranormal and supernatural claims, but let's turn it on science for a minute and ask, well, what about things like dark matter, dark energy, multiple universes, the multiverse? Think what was there before the Big Bang? What is the universe expanding into? Why is there something rather than nothing? How would you ever prove that or test those kinds of ideas?
So to me, as long as it's not testable, it actually doesn't pertain to science, right? Science has to make a hypothesis and say, okay, if this is true, this is what I'm going to find. If this is not true, this is what I'm not going to find. And so, especially what you were talking about, dark matter, dark energy. So we're seeing some effects. We don't understand those effects, but we basically say there must be an energy source that is accelerating the expansion of the universe beyond what we understand, because we wouldn't have an increase in the acceleration. So we don't know what it is yet, but we see the effect. And so this is science where you basically now try to figure out what it is, what it needs to be, what kind of characteristics it has. When you go to multiverses, we're starting to get into this really gray area, because if you're telling me that if there is a multiverse, I should have this many black holes or something like that, right? And if there's not a multiverse, I should have a different number, then that's a detectable or a provable theory. I can look at it and check it out. And so the multiverse is at this verge where, as long as we don't have anything that actually differentiates a cosmos with multiverses and not, I'll put it in the sci-fi bracket and say, like, I love the movies, but currently we have no understanding what difference it would make. And if it wouldn't make a difference, we are back at our invisible dragon in the garage.
Yeah. Make the same application to, are we living in a matrix? Even people that think we're living in a matrix, or they think it's a more than 50% probability on a Bayesian calculation that we're living in the matrix. Is there any way to actually test it? No. Oh, then what are we talking about? It's science fiction. It's fun. It'd make a good Star Trek episode, but beyond that, how is that part of science?
That's true. And the interesting thing is, like, you can still keep your eyes open, right? To see, like, oh, so can I now come up with prediction? Right now I can't, but maybe in 10 years or in 15 years with new detectors or with new instruments, I could. But for now, we have to shelf it with the dragon, with the sci-fi, and just keep it in the back of our mind in case we're starting to get a new instrumentation to probe it.
Okay, Alien Earth. This is an old idea. I recall reading Stephen Dick's book, The Plurality of Worlds is the title of the book, which is what this idea used to be called, right, centuries ago?
And so that great thing is, like, I agree. There were lots of people who were thinking about, are we alone or not? But what has just changed about a little more than a year ago is that we've put the James Webb Space Telescope in orbit. And for the first time ever, we have an instrument, a telescope big enough to get enough light from these small planets that could be like ours to figure out what the chemical makeup of the air there is. And if there's something I can only explain with life on these worlds. And one thing we found leading up to that is that 1 out of 5 stars has a planet that is not too close to the stars, so not too hot, not too far away from the stars, so not too cold. So in this, what we call habitable zone, where you could have liquid water on the surface of a rocky planet like the Earth. And so we have 1 out of 5, and we have 200 billion stars in our galaxy alone, and there are billions of galaxies after that. And of course, Carl Sagan never said billions and billions until he went to the interview, but we have billions of possibility right now. And this is where this idea of other worlds like ours is asking us, how could we tell? And so we need to understand our planet, its incredibly diversity of biota, and its evolution to get the best shot at not missing signs of life if they're out there, and we can, for the first time ever, collect them now.
Okay, hang on. Now let's back up for a second. So there's about 100 billion stars in the Milky Way galaxy, or maybe 200 billion.
Yeah.
And you're saying 1 in 5. Pretty much they all have planets, right? So
they all have planets.
How are you getting 1 out of 5, 20% are in the habitable zone?
So we know how many we found. It's about 40 within this habitable zone small enough to be a rock. And we know how good we are in finding it. So what you can do is to select for us to have found 40 with the equipment we have, that's not very good to do this. How many must exist for me to have found 40? And so this is how you get to 1 out of 5 stars must have such a planet, or I wouldn't have found that many yet.
I see. Okay, right. And approximately how many galaxies do we think there are in our known universe?
Maybe. Billions and billions.
But it's even I've seen a trillion, or at least
yes.
many hundreds of billions.
Exactly.
Yeah. Yeah.
I think at that point, it's a huge number. Whether or not it's now 200 billions, right, or 300 billions or a trillion, it's an incredible amount of galaxies. And each of those galaxies has like billions of stars with billions of worlds.
Yeah, I remember in Andreen's book, the last one, I think it was a companion to Cosmos, in which he talked about the formation of solar systems in the entire universe, that it would be 1 per second. So you snap your finger, new solar system, new solar system, new solar system. This is in the context of the argument, are we alone? Well, it's just really however improbable it is to go from the primordial soup to big brain communicating hominids like us. The number is so big. It just can't be that we're alone.
I think we're saying the bigger surprise, personally, for me, would be if we find nothing.
Yes,
because exactly like you said, if we have billions of opportunities and we find nothing, something really weird would be going on. And Andreen is such an amazing writer. So I loved her book too. And just like thinking about it, putting it in context like this, every second, snap your fingers, new system, new planetary system with its own worlds. What a world of possibilities.
Yeah. So we haven't found any yet. I mean, we found other planets, but not life yet. Why not? Is it because we're still so early in the process of searching and we've barely looked, and so it's too soon to say the absence of evidence is evidence of absence?
Exactly. What we were saying before is you need to know what kind of tools you have to figure out what the results mean. So what could you have found? And until we put the James Webb Space Telescope up into space, we had no means at all to find what's in the chemical makeup of a planet that could be like ours. And even now, it's at the verge of technical possibility. So the star has to be pretty close to us with its planet for us to catch enough light, even with this telescope that's so huge. But it's the first time ever that we're getting to the limit, or that we got over the limit, over the threshold, where we can now collect this light. And by adding it up, so every time when the planet goes in front of its star from our point of view, part of the stellar light gets filtered through the air of the planet before it gets to my telescope. And so when it hits a molecule, light is energy. And so when it hits a molecule, it can make that molecule swing and rotate. That means part of the light does not make it to my telescope if it hits such a molecule. And so the light that doesn't make it to my telescope tells me which molecules the light encountered on its road to me. And this is how we can read the composition of the air on another world. We did it already with Hubble for the big gaseous planets like Jupiter. But now for the small rocky planets, where the atmosphere is such a tiny sliver, and the comparison would be if you're an apple, the atmosphere of our world in the comparison of the size of the apple is actually smaller than the peel of an apple. That's the signal we're trying to get. And so we needed a huge telescope like the James Webb Space Telescope to even be able to collect enough light from the closest planets around the closest stars to do this. So absent of evidence just means we haven't had the tools yet to do this.
Yeah. It is astonishing you could do that. I mean, given how bright stars are, I mean, just take the latest eclipse, even at 99% blockage, it's still so bright. You cannot look at it without the filters. It has to be the 100% occlusion before you can take off your glasses and look at it with your naked eye. So, I mean, that a tiny, tiny little planet barely, I mean, how much of the light does it block? Like, 0.001% or something?
Yeah, it's tiny. And what we got really lucky, all of us, that the universe makes small stars and big stars. So 8 out of 10 stars are actually small red suns and not a big yellow sun like ours. But these small red suns actually form a lot of rocky planet like ours. And because the star is smaller compared to the planet, right? The planet's the same size as the Earth. If the star is huge, then the signal is tiny. But if the star is ever so smaller, then the signal that the same planet leaves is actually bigger. And we got lucky that Mother Nature basically makes rocky planets around these most abundant small red suns. And so all of these worlds that I told you about that are within the habitable zone and their rocks, they have a red sun in their sky because that's where currently we can find them.
Are they binary stars too?
Some of them are binary stars too. So you could have a double sunset and sunrise on some of these worlds.
Like in Star Wars.
And so, exactly, Tatooine right there.
Tatooine, right. Yeah.
But I was wondering where the second shadow is when you watch that.
Oh, good point. Maybe they didn't have a proper advisor to remind them to put that in there. Someone like you or Neil.
Yeah, exactly. So, I think Neil would have said like, no.
Yeah, that's funny. Well, okay, let's go back a little bit. Again, the plurality of worlds concept is old. Giordano Bruno famously got burned at the stake, in part for suggesting that there were other worlds. The other big part was he denied the Trinity of Jesus being a man and the Son of God and so on. Anyway, but it really wasn't until the 1990s, right, that you could actually detect an exoplanet. And how was that done? That was through the wobble or something like that? The wobbling
exactly.
of the star? Yeah.
And exactly, you pointed it out before, right? The star is so much bigger and so much brighter and also so much more massive. And so basically what for the first time became possible is to look at the movement of the star with such a high precision that you could see something tugging on it as small as a planet. And so we didn't see the planet itself, but we saw the star wobble back and forth. And it's like when you walk a dog and the dog goes in one direction, you really don't want to go, you lean back. And so the star moving back and forth again and again told you that something was moving around it. And you could estimate the mass. And thus you could say it's too small to burn nuclear fusion itself. So it's not a second star. It is a planet that goes around this star that I see wobble. And this is how they found the first star, the first planet around another star, 51 Pegasus b. And the really interesting thing was that they kind of knew how sensitive their instrument was. Again, they knew they could find a Jupiter. But Jupiter in our system needs more than 11 years to go around the sun. And so they were actually settling in for a decade of searching before finding a planet. And they found one in 4.5 days. So Monday morning to Friday afternoon, and the wobble was done, and the wobble started again. And so this is how we learned something we had not expected at all, that these big giant planets can actually move, they can migrate in some of the systems, because it's not very comfortable for the other small rocky worlds if this huge giant planet actually plowed through. But in some of the systems that happens, and these were the first planets we found because they're the easiest to find. They're huge and they're close to the star. But with more and more time, we found them further and further away from their sun, and so cooler and cooler. And we found smaller and smaller planets down to rocks like the Earth around small red stars at the right distance.
Amazing. Okay, now on the occlusion technology, that would depend entirely on just the sheer luck of it happening to pass between your telescope and the sun, that it can block a little bit of light. So those stars could have lots of planets, but they're not passing in front.
Exactly. And that is so exciting, isn't it? It's just we just see the tip of the iceberg, right? We have these thousands of new worlds, 5,500 already confirmed, more than 10,000 candidates. We're still vetting, make sure the detector works, that the telescope worked as intended. But we have thousands of new worlds, and we know because about 70% of them, so 7 out of 10, we actually found with this dimming of the light from their star when they go in front of us, that's just by chance. That's not even 10% of all the planets will do that because the alignment has to be just right. And so we know that what we find is just such a small fraction of what must be out there for us to find it. And this is in science, the really fascinating thing that I love is you get a glimpse into this huge diversity from just the few things you can see.
Mm-hmm. Okay, let's talk about solar system formation and why planets form at all. Is it the belief that there's a condensing cloud of gas, most of the matter goes into the star, and there's other little asymmetrical gravitational, whatever you call them, eddies, and those become planets? And what's the latest on that?
Absolutely. So it's a cloud of gas and everything in the universe moves. So it moved before it started to collapse. And the collapse could be indicated by a star exploding, and then you have like a density wave that collapses your cloud. And then if somewhere in the cloud there's just a little bit more material together, that will attract the surrounding material more. So in those clouds, there are actually hundreds to thousands of stars that form at the same times in different pockets of gravity. But they move too because everything moved. And so part of the material that doesn't fall into the star forms this disk around the star. And in that disk, the pieces collide and form bigger and bigger bodies, planets, sometimes rocks if they're close enough to the star, so it's too hot for gas and ice. Further away, where it's colder, you have rocks, gas, and ice. You get the huge giant planets like Jupiter or Saturn with the gorgeous rings. And then at one point, the star ignites the nuclear fusion in its core and blows out the disk. But the planets are much more massive, so they stick around and are then on stable orbits and keep going around that star.
And the configuration we have in our solar system, the rocky planets on the inside, the gaseous planets outside, or maybe some weirdos like Pluto that get captured or something, do you think that that's pretty much what you're going to find in other solar systems? Something like that. The numbers will vary, but
that's what we were expecting, right? And this is why these exoplanets were such a surprise, because we're saying, okay, you know what? The rocky planets will be close to the star because we understand that this is where they form, and the big planets out. And so the first planet, 51 Pegasus b, was a Jupiter, but in a less than a week orbit. Like it circled that star, its year was over in less than a week. And so then the scrambling started. But that's the most exciting time in science, when you see something that you didn't expect, because that means you learned something. Because if everything is like you expected, you don't learn anything new. And so this is how we learned that these, as long as the disk is around, these planets can actually move position because the disk can actually slow them down. And there's a certain gravitational pull from the star. And if you don't have enough speed, that means you will move towards the star because the gravity is just stronger until this stabilizes, right? So the speed is just enough to counter the gravity, then you stay where you are. And so we learned that planets can migrate. And we learned that from finding other systems. So is our system unique? We don't know yet, because finding our system is incredibly hard. And Jupiter needs like more than 11 years, right? And that's our first gas giants. Then you have Saturn and the other planets. And so we didn't have enough time yet to find a system like ours. What we did find, again, a bias, because it's easier to find, are stars that are very close, have planets that are very close to them, because they're faster to find. And so we're finding this huge diversity of planets and also this huge diversity of rocky worlds. So some of them take not even 18 hours to go around their stars. So the year is less than 18 Earth hours. And we know it must be so hot on these rocky worlds that they would be covered in oceans of magma. And just imagine such a world. We wouldn't have imagined it before we went searching. And that's the best part of science, finding things that just expand your horizon.
Okay, so back up for a second, make sure I understand this. A large gaseous Jupiter-like planet forms where our Jupiter did, about that distance, and then it migrates in for some other reasons, whatever those are, and that's why you end up there. And so the last one you described would be like Mercury being what, 50 times closer than it is, something like that?
Exactly. So close that every rock we know would just got baked by the heat of the sun to the point where it would actually liquefy. And it's really interesting because of these planets, we actually get the first data now with the James Webb Space Telescope to see the light from those worlds. And we are now saying, okay,
You mean
for
the
example,
reflected
here at the
light from the sun on the planet, and you can see that?
and also the emitted light because it's so hot.
Oh, I
You
see.
have thousands of degrees. And so we have a lava world lab here that we founded at Cornell, from the Carl Sagan Institute. We produced this idea of, you know, how do we even know what the lava is made out of? And so what we do in the lab is we actually mix different things together, like more iron, less iron that we have here, and different chemicals, and then check what the light would be if you heat it up to 2000 degrees, to have a comparison chart to the observations now with the James Webb Space Telescope of these new worlds.
Oh, that's so interesting. So it's a little bit like the spectrograph where you take the atomic signature of the light from a star and infer what it's made out of based on heating things up on Earth and what spectral lines they give.
Exactly.
Okay.
And so we need to know much more because we've done stellar physics or we've observed stars for such a long time that we're quite comfortable with that concept. But we didn't know that there would be rocky worlds so close to the star that they would be completely covered in lava. So we don't have that data. So we have to do it in the lab to have anything to compare it to, because on the Earth, our lava is whatever the composition of our rock is. But out there, it could be different. And because we can catch the light of these worlds now, we can actually check what they are made out of. What is really fascinating.
All this is astonishing to me, just theoretically, but at some point, engineers are designing these machines and computer programs to analyze the data that comes in. Talk a little bit about how that's done and who does all this. There must be teams of people that do this.
Absolutely. There are teams worldwide. So we have bright ideas completely all over the globe. So this is not an American thing or European thing. Everybody, and even if people work in America now, a lot of them are international from all corners of the world, pulling together their ideas and their capabilities to figure this out. And so what do we do? Probably like most people, most of us sit at the computer. And the way to think about this is that what I do, for example, is a little bit like weather prediction. So I have a model for the whole planet, and I know how much heat or how much light from the sun actually hits it. And then I know what the planet's made out of. I can choose that and whether it has life or not. And then I create this world on my computer, like you would create a weather forecast, just with a different sun and with like more mass, like more gravity or less gravity, more water, less water, whatever you want. And then that will tell me when I do the light fingerprint of that world, what it would look like in my telescope. And now I have counterparts that take the light that we get from the James Webb Space Telescope and analyze it, basically have a look how bright it is at the different wavelengths. For example, how bright is it in the red? How bright is it in the blue? And then we cross compare. We basically say, okay, so this looks like these models, or like the planet is like that. And you connect that with a computer program. And you also use artificial intelligence at that programming, and use Bayesian statistics. So a lot of tools we've developed for many different scientific options to take the light that the space telescope collects, sends down to us, to filter it, to make sure that everything's fine, and then to figure out what's in that air, and then to figure out what does that mean. So it's a chain of many, many people with many, many expertise who make the answer.
How do you get time on the James Webb Space Telescope? You just call up and go, "Hi, it's Lisa. I was wondering if I could use the telescope next weekend."
I wish, I really wish that how it would work. And I think if it says like it's Lisa, that should really give extra time. I completely agree with you. The way it works is that we have to write a proposal. So we say, look, we would like to use the James Webb Space Telescope for X numbers of hours. And we need these, let's say, 10 hours, because if I look at this planet for 10 hours, I'll be able to tell you whether or not there's like CO2 in its atmosphere or not, for example. And so you describe your research, why it's important to do, and how much time you would need on the telescope, when you need it. And then there's a gremium of scientists that volunteer to actually evaluate all these proposals. And you cannot be on a proposal if you evaluate, right? Because that would be a conflict of interest. And I would say like, oh, Lisa's proposal is really what we should do, right? And I shouldn't be doing that because that wouldn't be okay. But the James Webb Space Telescope also does black holes and galaxies and other things, that I don't understand why anybody would be interested in that
Yeah,
if you
sure.
could find signs of life. No, I completely get that. And so they're finding a balance. They're finding a balance between the topics and the secrets of the universe we want to unravel. And then they select among these proposals, and they are way more than there's time to say, okay, this one is really important to do now and will give us like answers that we can then use in the next year. So you can propose once a year for time on the James Webb Space Telescope. And usually all these teams are mixed too. So it's not one person who proposes, it's like 20 people, 50 people who say, look, this is the most important thing to do. And this person will do what we call the pipeline. It will actually analyze the light that comes through. This person will do the modeling that actually then tells you what it means. And so it's a lot of people coming together to give the most compelling story of why you should give this precious time on a space telescope that is limited because at one point it won't observe anymore, to this project and what it will tell you.
What's the lifespan of the James Webb supposed to be?
There we have great news. It was supposed to be 5 years, but the launch was so perfectly executed that they didn't use, it's limited by the propellant that moves the telescope and points it in different direction. And so they were making it, designing it for a minimum lifetime of 5 years. But the launch was so perfectly executed that we probably going to get 15 to 20 years out of it because they could save so much fuel. And that has expanded our horizon because it's not like a frenzy where like, oh my God, in this in 4 years, it's going to be gone and I'm not going to get any more data. Now we have a little bit more of a horizon before the fuel runs out. So we can do more. And everybody was hoping for that. But, it actually materialized in that for all the scientists, whatever you're excited about in the cosmos.
And I forget how big the mirror is, or is it a series of mirrors or?
It's 6 meters, 6.5 meters. And it's basically 4 times me or 4 times you, just put together on top. That's the diameter of the mirror. And you cannot put that in a rocket, right? Because we don't have any rocket that's that big. So they had to fold it. And so this was one of the scariest things for anyone working on this and hoping to use the telescope, that they had to unfold it in space and all of it had to work. And it did, right? I could believe, engineering is amazing, but it did. It actually did. They had like 136 single points of failure. So if that goes wrong, then we can't use the telescope. And all of them went right. They had backups too, but all of them went right. And that was just such a relief when we got the first pictures, because until you take the first pictures, you cannot say if everything worked. And so then did the first engineering pictures where they just test if it actually does what it's supposed to do. And it was like a relief all over the globe because people were like, oh my God, it really worked.
And what comes next after the James Webb? Isn't it a land base down in South America? And the Atacama Desert or something? They're building a huge one?
They're building a huge one. It's called the Extremely Large Telescope. It's built by the Europeans. The European South Observatory is the home institution. And basically, it's a 40-meter telescope. So that's huge, really, really huge. And the funny part about this is like the Extremely Large Telescope, they've broken ground. They're going to start to observe in 2027. It's not that far away. The Extremely Large Telescope. And then the next concept for something bigger than that is called OWL, the Overwhelming Large Telescope. And then we're done with naming. The next generation has to find a better name than that.
Well, you can do
And of
you
course,
can do the whole Elon thing. What the big fucking rocket? What did he call it? The large fucking rocket or something like that.
I know.
Yeah.
But when you have like some public funding, it's harder to actually
Yes, of
come up
course.
with
Right.
weird names.
But the idea there, putting it at the top of the mountain, is to get above the water level, right? So you're looking
The
through less
further
stuff.
you go, the further you go up and the more you can go in a desert, the less water you have, and hopefully also the less clouds you get. So the more of an unobstructed view you have looking out into the galaxy. And of course, in the US, we also building or thinking about building this big telescope that's called the TNT or the GMT. But we don't have the funding for that one yet. And so the ELT, the extremely large telescope from the European side, is going to be our next telescope, our next instrument. And then wherever we can build something even larger than that.
Hmm. I visited one down in South America in 2009 on the bicentennial of Darwin's
Hmm.
birth and the 150th anniversary of the origin of species. I was lecturing there, and I met an astronomer. He took me to the top of the mountain, at the Atacama Desert. There were 4
Hmm.
telescopes up there. I forget the name of that one now.
I think it's the
The
VLT.
VLT,
They're
yeah, that was
basically,
it. Yeah, it was
they're
unbelievable. And I got to go in the dome, and it's like, well, where's the eyepiece? Eyepiece.
eyepiece. Yeah, it's just like why would we waste anything on
Yeah,
eyepiece? It's like this romantic notion that I get to look through a
right.
telescope. It's the same thing. We want to take a picture with our digital camera, right? We don't want anybody just looking through it and trying to graph it. We want to take the picture, and the same we do for the universe because it captures that information, it digitalizes it, and so we can analyze it really
Yeah.
easy, no matter how good you see.
Okay, so the planet's passing between you and the sun. You're gathering some data from the atmosphere, and you're picking up what? Oxygen or CO2 gases, or there's an ozone layer. And how do you distinguish between what could be naturally caused and then what could be caused by living organisms there?
That is the great question. How can we make sure that there's a difference, or how do we know there's a difference between a planet with a thriving biosphere and a planet without? And so when we look at the Earth and its history, we had a thriving biosphere for a while, but only about 2 billion years ago did the biosphere produce oxygen as a waste gas. And the combination of oxygen with a reducing gas like methane, because methane plus oxygen reacts to CO2 and water. The combination of these two gases, oxygen and methane, tell you that something is producing these two gases in big amounts. Methane could also be out of a volcano, but oxygen in big amounts right now, because it reacts with methane, we only have an explanation for this to be life if the planet is nice and warm. So what we're trying to do is to understand the circumstances. Like, is the planet hot? Is it cold? And then see the combination of gases, oxygen and methane. And that's, when looking at the Earth, is our golden light fingerprint for life. And that's what we're trying to find somewhere else. But for the first time ever, we have a telescope that can collect enough light to find it. And so, for example, CO2, if it's in the atmosphere, leaves a bigger signal than, for example, ozone or oxygen. So what should happen, or what will happen, is that you'll hear a lot of, oh, we found CO2 in the atmosphere of this world. Oh, we found water. Before you hear, oh, we found oxygen, or we found oxygen in combination with methane. So we're going step by step to analyze these planets. And of course, there's lots of beautiful, big, giant planets or big, hot, puffy planets that don't have life, but they're also really interesting to look at to figure out what they are made out of and if they're similar to Jupiter and Saturn or very different.
In other words, it's something of a signal detection problem. The signals coming in, do they indicate living organisms made those gases, or volcanoes, or whatever natural processes? Do you have an algorithm or a model or something that says that's the one, that is it right there? We have a hit.
Exactly. That's basically what my research is all about. My research is all about running these models, these atmosphere models, these planetary models, and telling which ones have signs that I can't explain without life. And then looking at the light from the telescope and figure out if I have a match. And so we're building this database of light fingerprints of living worlds and light fingerprint of dead worlds. And then there's a gray zone in between where it could be a living world, but I do not uniquely have signals that tell me either way. So we'll have this big parameter space. And the good thing is we have billions of options. So hopefully some will fall here, some in the gray zone, and some in the other worlds.
Okay, let's flip the perspective and let's say there's astronomers going around the planet at Vega, because I think Vega was in Star Trek, one of those episodes. I don't know, 1,000 light years away, whatever
And
it is.
also in Contact.
Oh, in Contact, that's right, it was Vega. Yeah. Oh, let's make it Vega in Contact. And they turn their telescope and the Earth passes between them and our sun. What would they see? Or what data would they get from us?
Absolutely. So this is one of the first papers I ever wrote, one of the first scientific articles I ever wrote, saying, what about somebody else looking? What could you see in the Earth? And I wrote it saying like, so if we know what we can see in the Earth, then we know what we need to look for. And then I basically made the Earth younger, because the Earth has changed significantly, right? Since it was young, there was no oxygen initially, then oxygen came on, then more advanced life started. And so what they would see is the combination. If they saw us right now, right? You have 1,000 years, so it's okay. 1,000 light years. Light needs 1,000 years to get there. So they would see 21% of oxygen. So they would see the oxygen in the ozone line because we have an ozone layer. They would see the methane line because there's methane in our air. There's water in our air. There's CO2 in our air. And so they could actually piece that together and say, oh my God, I'm looking at a world with a biosphere. And they could have done so for about 2 billion years. That was the question I asked myself when I was a student. How long would that actually hold, this light life fingerprint? And so for the Earth, it's about 2 billion years back in time where you still have the combination of oxygen and methane. Before that, there was life, but life produced methane or CO2. So it's not a unique sign. And following Carl Sagan, extraordinary claims need extraordinary evidence. So you're not just guessing that there could be life. You should have no other explanation than there's life. So that's what they would see. And what's really interesting too in that aspect, I was at one point when you're doing this research, right? You're thinking about this and where you could find life in the universe. I was thinking, well, actually, where are we the aliens? If there's life out there, who could be seeing us, spotting us, our planet, block out light from the sun, and the sunlight filtering through our air? And so if you go out to about 300 light years distance, so light needs up to 300 years to go out there, and the reverse, the furthermost planets would see the Earth like it was 300 years ago, and we would see them as they were 300 years ago. Then you get about 2,000 stars who have this perfect vantage point to see us block light from our sun. And for about 75 of those, they are within 100 light years. And what that means is the radio waves that we started to send out about 100 years ago would have already washed over those worlds as well. For better and for worse, because, music tastes change through time.
Yeah.
Exactly.
What about the what is it? The square, the energy dissipates by the square of the distance or something like that. So these radio signals, which are already pretty weak, the further out they go, is it get weaker and weaker?
Yes, absolutely. It goes for radio waves and it goes for light. And this is why the closer the star and the planet is, the more of the light we can catch. Because when you're twice as far away from a star and the planet or from a light source, if you're twice as far away from a light source, you get only a quarter of the light. If you're 3 times as far away, you get only a ninth of the light. So it goes down fast, as you said, with the distance squared. And so the closer, the better, because the more information we can tease out of the light we get, because we can split it up in its color, as you said, spectroscopy. So we basically use the white light and like a rainbow, we basically split it in its colors and see if there's enough energy in each of the colors or if there's some energy missing. And the missing energy tells me what molecules it basically hit. And I know that because I can go to the lab and have a canister filled with water vapor, shine light in on one side, and figure out on the other side what doesn't get through. And so I look at the light from the planet and compare it to my database and say, oh, that's CO2. Oh, that's oxygen. And this is how, even though we don't have the ships yet to get there, I would love a Star Trek, Starship Enterprise. I'm all there because it goes fast and it could explore all these different worlds. But even though we don't have it, we get to explore these other worlds because we can catch the light and decipher the information in it.
And remind us on what there is at Proxima Centauri. There's two different planets we found there, and are they close enough to get a little tiny spaceship out there at near the speed of light so we can get the data back in time to see what's going on?
That's definitely what we're trying to do. And there's this idea of the star shot,
Yeah.
where we're basically trying to come up, and it's not science fiction, it's an engineering problem. Really, if you think about it, all of it is a kind of engineering problem. As long as you don't want to send humans, because as soon as you want to send humans, it becomes a lot more complicated because the times involved are really long. And then also you have to sustain that human, right? We don't want to kill anyone. We want to actually get people there and back. And so if you think about a chip, and this is the idea of the star shot idea, you could have like a tiny chip like you have in your cell phone and give it a huge push, like put a sail in front of it from a lightweight material, give it a push with lasers and speed it up to, let's say, 10% the speed of light. And Proxima Centauri, one of the three systems in the Alpha Centauri, Alpha Centauri A, B, and C, so Proxima Centauri C, and our closest star, about 4 light years away from us. That one, if you could go with 10% the speed of light, you get there in a couple of decades. But there's a lot of issues with them. A, having a material that can actually take that bounce, that push, and also you would be going so fast, you have to turn the camera on just at the right moment or you've flown past. And so the exciting thing is that it's an engineering issue because even our closest star after the sun has a planet in this habitable zone that could potentially be like ours. And I think that's just amazing because it will always top any travel list just because it's the closest.
That Star Shot, that's one of those Russian oligarchs funding it, right? So they have the money's there
Exactly.
to actually make this happen.
I think the money is there to think about it and the money is there to develop the concept. But to really bring all the pieces together, you need a huge battery that actually can store that energy. You need to build those lasers. You need to build that material. That's going to take time and that's going to take an investment. But I think there's a lot of things that can come out of it that would be economical viable. Like, for example, big batteries that store a lot of energy, right? That's something that we're probably going to need anyway. So I think it's a smart allocation of resources for something that we might use anyway, that you can actually monetize anyway. But it's just one idea of how to get to the next star. But until we have it, we're catching the light that goes through the
Yeah.
universe for
We
free
need you
and read
before
it.
we could go there, getting the information from light. Yeah. So let's talk for a moment about the vast distances of space. It's just astonishing how long it would take. I mean, you just start decades to get to the closest star at 10% the speed of light. If Voyager was going there, and it's
Oh,
hauling ass, right? It's going like 40,000 miles an hour or something like that. It would take something, what was it, 70,000 years to get there? I mean, it's just
even more, yeah. It's
astonishing. There's
crazy.
just mostly empty space. There's just mostly nothing.
When you take our sun and the 8 planets and shrink it to the size of a cookie, then the next star over, Proxima Centauri, the 4 light years away, in the same scale, is about 4 football fields away. That's how vast space is and how big those distances are. But if you turn it around, so we are a tiny planet in this cookie, right? And we're trying to go, we went to the moon, we're trying to go to Mars with people, like we went to Mars with robots. But we have figured out that there are other stars, that there are other planets, how we fit into our galaxy, and even because light has a speed limit, so it takes light time to get to different distances. What that means is the further away we look from us, the further back in time we see. So we can even figure out how the universe was when it was young and how it started Even so, our planet and our star was not around. We missed 2/3 of the whole evolution of the universe, right? Universe about 13.7 billion years old. We are about 4.6. But because we can unravel and we figured out that the further away we look, the older we see or the younger we see the universe, so the more we look back in time, we can actually figure out how our whole cosmos started. And that gives me hope for us, like generally, that we can figure out whatever we need to figure out, to fix climate change, to do other things, because we have figured this out, a normal planet around a normal star, and we figured out how we fit into the cosmos, and we're still looking.
Other examples I heard was that if Andromeda Galaxy, which is going to collide with the Milky Way, if they pass through each other, the space between the stars is so vast that there'd probably be little to no collisions at all, stellar collisions.
Exactly. And that is so mind-blowing in a way, right? It's like, oh, two galaxies collide, and you're like, oh my God, this is going to be terrible. There's going to be all these explosions. But cookie, football fields. So if the other star with its planets, the other cookie, has a lot of space that it can go through without hitting anything. And that's what should happen when two galaxies collide.
Yeah. And then I think it was Avi Loeb who said this, that to get to another galaxy other than Andromeda that's coming at us, because they're all expanding away from us, no chemical rocket could do it because the expansion of the galaxies is faster than any chemical rocket could go. Is that true?
I think the chemical rocket, I give you. But as you were talking about before, is we're trying to figure out how we can get to fractions of the speed of light. And those fractions of the speed of light, maybe it's going to be a laser pulse, maybe it's going to be a solar sail, right? That just basically augments the speed faster and faster and faster. I think there are other ways that we can go, but we just don't have the engineering capabilities yet. We're thinking about them. And so that we can't do it with a normal chemical rocket is actually not something that I'm very worried about. And also, I'm okay. I want to go to the planets in our solar system.
One
Let's
step
do
at a time,
steps.
yeah.
And then to
Okay.
the next star, because
Yeah.
even that has a cool planet. Before I even want to consider like other galaxies, we have lots to do. 200 billion stars with their planets in our galaxy alone. I don't need to go to the next galaxy yet.
Okay, bring us up to speed on the origins of life theories, the different models that people have proposed. I haven't read this material in maybe 10, 15 years, so I'm behind. What's the latest on where it likely originated here on Earth, and then what you would look for on some other planet for those kind of conditions where it might have happened?
Well, the debate is as lively as it was 10 years ago, maybe a bit more lively now. But the consensus so far is that you need a surface where different molecules can actually stuck to create something like a vesicle or a protocell. What it basically just means is that the ocean or water is incredibly good in diluting chemistry. And to get life started, you want to get chemistry concentrated to make these structures like a DNA or something, RNA, whatever you want, proteins. And so we think that you need a kind of structure, whether that's a cylinder, like for example, on the bottom of the ocean, where these black smoke gush out these really, really hot and mineral-rich waters. And so then if you had a cylinder structure there, then you would have a temperature gradient there that could help you with actually getting the chemistry concentrated and getting chemical reaction started. The other idea is a shallow lake. That's the shallow pond that Darwin was favoring. And that's basically where on the bottom you could again get like these different atoms and molecules to stick together and form a kind of structure. And then as soon as you have the structure, you can actually selectively let chemistry in and out. The other idea that's still in play too is ice, like big layers of ice, because when something freezes, you also can concentrate the chemistry in the residual water. And then when it gets hotter again, you would actually pollute it again or get more water in and get more material in. So the story is that we don't know where life got started, still 10 years after, because we cannot make life in the lab. If we could, then we could actually say, oh, this works and this doesn't. But it's absolutely possible that life can get started in many different ways. And then it might even have started in many different ways on the Earth, but then one form became dominant. And so we only see the survivors. And so this idea of the tree of life that we all have, or that I have from university, is actually very misleading. It's a beautiful idea. I love the tree, but it's mostly a net with lots of different stems. And then the circumstances just happen to favor one, and that one is the one that we then finally see blossoming. And so if the circumstances were different, the chances are very high that a different form of life would have taken advantage of that and become the dominant life form. And so that's the consensus right now about the origin of life. So what do I look for? A biosphere that changed the planet so I can see it in the light. Because if the biosphere does not change the planet, I have no way of telling, as you were saying before, whether the planet has life or not. But the biosphere changing was 2 billion years already on our planet, so about half its lifetime. And then, of course, you can always go and look for signals, hoping that somebody would want to communicate with us. And that's, of course, what the search for extraterrestrial intelligence is doing, trying to search the whole sky for signals. And there, the problem you pointed out before is the loudest whisper the loudest scream will turn into an imperceivable whisper at a certain distance. And imperceivable depends on how big the telescopes you are that try to catch that whisper.
By the way, what happened to the Arecibo telescope? Was it just a structural failure?
It was a structural failure, and it was a disastrous structural failure, but luckily it was one after another, so they could clear out the whole telescope. And they were trying to fix that structure that kind of that iron thing that failed, that was holding the telescope, one of the pieces. But once one fell, theoretically they had two and there was a backup, but once one actually was structurally compromised, then it actually pulled very much on the second one, and then that broke too, and that collapsed the whole telescope. But luckily nobody was there, so they had cleared it all out, so there was no loss of human life. But of course, it's a devastation, especially for people, scientists there who were using that telescope.
Isn't there a big one like that in China?
It's called FAST. And so they built one that's even bigger than they built one that's even bigger than Arecibo. And so what they can do thus, first it's bigger, but they can also use part only of that radio dish. And so they can basically steer. If they only use this part, they look this way. If they only use this part, they look up. If they only use this part, they look this way. And so it's a more directed approach than if you use your whole telescope and then you look wherever the Earth is rotating, so wherever you're pointing. And so this is one of the advantages of an even bigger telescope. And so they've built one in China, and it's called FAST, and it's doing an amazing science.
Yeah. Okay, well, SETI is always looking for these radio signals, and there's Jodie Foster on the hood of her car with the cans on her ears and gets the signal. Of course, that's not exactly how it works, right?
No, so everything has changed insofar that whatever we do too, right? Just take your camera, right? We're not using film anymore, we use digital. And so that's what we do in any search, whether it's the search that I do in the light, trying to find biosignature or signs of a biosphere on a planet in the light, or that SETI is doing, trying to figure out if some of the radio signals could be non-natural. So the computer records it, and then we have programs written that look for signals that are out of the norm, out of the ordinary, or that follow a specific pattern that we want to look for, whether it's in the light or whether it's in the sound. And that's basically the romance of astronomy, is now sitting in front of your computer and seeing that on the computer. But we usually don't get the headphones anymore. But you could always say, like, okay, now I write another program that actually translates those signs into sounds and then basically go that way. But we're not doing sounds first, identifying something, and then checking. We're doing checking first. And then if you want, we can go back into old school sounds.
Right. So in context, Sagan famously put the series of prime numbers because there's nothing in nature that would replicate prime numbers. Are you sure? Because I remember Richard Dawkins pointing out that nature does produce Fibonacci sequence numbers, like the spiral of a pine cone, that kind of thing. So are you confident that, and what are some of the other signals that would constitute something non-natural?
So basically, what we are looking for is like we have looked at many different places in different galaxies. And so we know the patterns that like normal stars or pulsating stars are doing. And some are incredibly predictable, like the leftover core of a dead star. A star explodes and you can see the leftover core very hot and it gives pulses. So we basically know a lot of different objects, and none of them that actually sends out light or pulsates would or has so far recreated the prime number sequence. And the hope is also that you would have a prime number sequence that would go up like, predictably and then reset, and then predictably and reset, because that's something that naturally you can't explain, like, that it would go up, 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 maybe, but that it actually would reset and start from one again, that's intentional. But the really interesting thing that I think about a lot is like, first, we want to just have a signal that tells us there could be life on another world, because that opens all these opportunities to think about, do you want to communicate? What could it mean? And so on. But it's kind of funny to me that we expect that we would understand the communication. Because if you just think about how many different species are on planet, we cannot communicate with many of those. And in my book, I just use this example of a jellyfish, or in my class, I use a jellyfish. Have you ever talked to a jellyfish? Like, I try it, I can't do it. So in a way, if a message would come in jellyfish language, I think we would be in big trouble trying to decipher it.
Oh, that's like an Arrival, because you wrote about Arrival, right?
Exactly. I love the idea about Arrival, where they just took that concept and put it a little bit on its head. So he's an amazing writer. And so he was basically saying, well, then we have to learn that language, and it might not even be in the same way that we think about it. So he used time. But that is absolutely true, because communication, even, between people who know each other, sometimes is fraught with misunderstanding, let alone between species.
Yeah. Yes, well, no offense, but it was nice that it was a linguist who was the hero of the story instead of a physicist.
Absolutely.
It's always a physicist. How about give the social scientists a chance? Yeah,
I
because
think they will need to be included.
Yeah,
Absolutely.
because Sagan famously joined the Order of the Dolphin, or I think he was one of the founders with John C. Lilly. Can we even talk to dolphins? They're mammals. They're right here on Earth, and we don't even know what they're saying. How are you going to talk to the aliens? So so John C. Lilly famously just gave him acid.
Probably not the best choice if we ever were to find a different species, because we don't know how they would react to that.
But it's a huge problem, even if you've discovered that there is a signal. Okay, so talk then about, so you're looking for biosignatures. Talk about technological, what are they called? Technosignatures, right? Something like a Dyson sphere or something like that.
So basically, if you think about the life on this Earth, or the evolution of the Earth, the history of this Earth in a 24-hour clock, then the first signs of life were around 5 a.m., so 3.5 billion years ago. And around noon, you have the buildup of oxygen with this reducing gas, so you could find life that way. But less than a fraction before midnight, less than a second before midnight, you have us coming on the cosmic arena. And then even much, much less than that, we're talking about 4.6 billion years, right? You have radio signals. That's about 100 years ago in this huge time scale of life on the Earth. But it is absolutely true that we have no idea how long it's going to go into the future. And if you are looking for a gas combination, you can't tell what's making that gas. Is it you and me? Is it a dinosaur? Is it a dolphin? Is it a single cellular life? And so if you were to get a technosignature, whether it is a communication radio signal that says, hello, hi, we're here too, or it is some kind of huge structure that harnesses energy, like a Dyson sphere, from additional energy from another star, that basically shows you that a civilization became technologically so evolved that it can fulfill all its need for energy without polluting its planet. That is, of course, a fascinating concept to consider that could happen. Or people have thought about, what about space art? What about if somebody says, oh, somebody's going to look at us, so I'm going to put like a huge sculpture in space, then that's going to look really weird if
The
it goes in front of
monolith.
the star. Yes, the monolith, exactly, the monolith. But that one had the big problem that it's completely black, right?
Yeah.
So it's not reflecting anything. But I could see the shadow. I completely agree. And so there you go into the amazing realm of science fiction. And I try to unpack a lot of the things like which planets could be real, because I think the science fiction actually takes us from where science needs to stop because we have no more information and takes us in the realm of interesting, curious possibilities that could exist. And so a Dyson sphere, art in space, a kind of huge spaceship that goes, through the whole universe. All of these are things that would be interesting to look for, but we do not know what we would look for because we have our imagination that says, okay, maybe that could be a monolith, right? And that is very much inspired from science fiction work, but we haven't found anything yet, and we haven't made anything yet. So that means, what are you going to search for? And so what we do is we search for signs of life and we keep our eyes open for interesting, unexplained kind of signals, and then try to figure out if we can explain them, like focusing on it and say like, oh, actually, it's not as weird as we thought it was, or if it stays weird and if it stays interesting and if it could indicate some kind of technological advance.
Remember from a few years ago that story about Tabby's star? Tabitha, I forget her last name, made that discovery. Maybe it was comets or meteors or a bunch of planets or debris, or maybe it was something like a solar panel sequence going around the star or something like that. I remember I went on KBC Talk Radio with John and Jillian to talk about this and other UFO related stuff. And they were talking about Tabby Star, 1,500 light years away it was. So Jillian, the co-host, goes, well, what are they like? It's like, what are who like? The aliens. It's like, well, okay. All we have is a dip in the light. We don't know what it is.
There's a huge jump from a dip in the light that is kind of weird to...
But this is the jump everybody makes, okay, in the media, in the popular culture. Mm-hmm. I'm part of the Galileo project with Avi Loeb. I like Avi a lot. He is massively in demand. He has camera crews like at his Harvard office every day. Why are they there? And I contend it's not because he's doing the kind of research you're doing, looking for some signal in the data or something like that. He thinks that we've made contact or there's a good chance the aliens are there. It's the aliens, that part of the story that seems to just grab everybody's attention. Why is that? I mean, certainly that, the Sagan effect, I mean, that's part of it because everybody's fascinated by aliens.
I think we are curious by nature. This is one of the things that defines us as human, right? Whether it's curious about science or we're curious about why the person is laughing at the other table, I would like to laugh too, right? And we love connection. We are social creatures. And I think that combination is beautifully served because we've explored a lot of our planet already. And now we know that these stars that we see every night also have their own planets. And we're starting to wonder if maybe there's something there that we could connect to too, that makes the loneliness of the cosmos easier to take, as Carl Sagan was writing about. And I think this is our new frontier and this hope that in this vastness of space, we are not alone. We are not special. I think is underpinning this happiness or this love of people for aliens. And what is so great is that we at the verge of figuring it out, that we live in a time where for the first time we have an instrument, a telescope, the James Webb Space Telescope, who can do this. And I think I always wanted to live in a time where we saw the moon landing, but I've given up on this because I want to live in a time where we get the signals back and figure out that we're not alone.
Yeah. Well, Carl made that point that it's a kind of almost a religious impulse or something that resembles that religious sense that there's something out there that's vastly superior to us. And if we did encounter extraterrestrial intelligences, they would not be just close to us in culture and technological scientific development. They like at Roswell. Oh, they landed in Roswell and we back engineered, and that's where we got computers and silicon chips from. Really, they were just 5 years ahead of us. I mean, they're going to be
exactly.
5 million
can we see
years ahead
ourselves?
of. Yeah.
Can we see ourselves in 5 years going to the next star? No way.
Yeah.
And that Terry Pratchett made it so nicely, like when he said like sufficiently advanced technology is indistinguishable from magic, right? For us or for somebody 100 years ago, if I take out my cell phone, magic, flashlight, magic,
right. Well, with the guy with the brain implant that can move the cursor on his computer and play games and so on. If you didn't know he has a chip, it looks like telekinesis, right? It looks like paranormal superpower. But back to this concept, I wrote a couple of my Scientific American columns. One was deities for atheists, and the other one sky gods for skeptics. Sort of playing on words, but the idea that if I wrote about Clay Routledge's research on this, that people that are high in need of awe, they get inspired by they feel awe when they go out in nature and so on, or the eclipse, whatever. But they're low in religiosity. They don't believe in God, or they're not religious. Are more likely to think that aliens are out there, and so on, and the reverse of that as well. If you already believe in God and that's your awe, then you don't need to believe in aliens. And that I think Carl was right about that. That there's something. It's not that what you're doing is related to religion or anything like that. It's just that the drive behind it. Why do we want to know that we're not alone? And again, back to what the aliens would be like. They would be indistinguishable from omniscient, omnipotent, maybe even omnibenevolent. Maybe they figured out how to not nuke each other and ruin their planet and so on. They're more morally superior to us so much that they appear to be omnibenevolent. So what would you call those beings? You'd call them gods, or if it's a natural explanation, they're just super advanced aliens. I think it's the same impulse.
I think you exactly put it to the point that in our imagination, we can only go a little bit further than what we are, right? And so people are like, oh, if this is UFOs, yes, we got like the computers from or so, but it wouldn't be, because if you travel from one star to the next, the leap in technology is so significant from what we have right now that you wouldn't be able to back engineer it, because you wouldn't have anything in between that you could back engineer, right? You cannot just jump 10,000 years into the future technology-wise. You have to go through it. And there's this other idea that, a lot of people say, well, if there's so many people, or if there's so many planets out there that could have life, then where's everyone?
Yeah.
Right? So Fermi's paradox.
Yeah.
But when you look at this question in more detail, the underlying assumption in that question is that anybody who would find us would immediately want to come and talk to us. And my question is, why? What would you learn from us? Like, the Earth is my favorite planet, not even a question. But if I could pick from several planets with life, I would pick a more advanced one, right? Just to learn, to figure something out, to how did you survive? That's what Contact is asking, like, how did you make it? But when you turn this around, then it's actually not very surprising that we have nobody who comes and visits us.
So that would be the zoo hypothesis, that they're just observing us but not interacting with us. But then there's the
question is if they're even observing, right?
Yeah, or maybe they don't
have
care.
Things to pick from.
My answer to the Fermi paradox is that they're probably out there. There's probably not that many of them, and there's so much vast space between them. They just haven't found us. Mm-hmm. And but of course there could be the great filter. Maybe they nuke each other or they ruin their planet. But everything you've told me so far today makes me also think about the timing. What if it's just the timing? It's just they were a million years ago looking, or it'll be a million years from now and we'll be gone, and that we'll just miss each other.
And so I agree with you. And this is why I focus on this passive search for signs of life in the air, because then that doesn't require a civilization or any life form that wants to communicate. Because we haven't made up our mind either. We don't know if we want to communicate, and that's perfectly fair, because we have to all get our mind together and figure out if we would want to communicate or not. And so basically, I think the search for signs of life in the air uncouples us from this need to find a civilization that also wants to talk to us, and to talk right now. And there is the time component between us. And maybe we're going to get to a stage where we don't care anymore about other planets because we have other things to do. And so lining up the time where we're just curious about each other is probably a very hard thing to do, even if we have millions of habitable worlds with civilizations. And that's just a hypothesis, right? I'm giving you way more because we've billions of possibilities. And we haven't even talked about moons that could be life, habitats, so just the sheer number of planets at the right point that are rocks tell you that the number is forever in our favor, that there could be something out there. But lining up the interest and also making an assumption about the curiosity level of a completely different life form, that I think we have no base on. But searching passively for signs that a biosphere would leave in the atmosphere of a planet divorces our search from that communication need or from that lining up of two civilizations wanting to talk to each other.
Yeah. The idea of panspermia, not directed, but just accidental, like the Mars rock that they found in Antarctica. Is that a possibility in your scientific models? Earth was
Absolutely.
seeded?
But I actually think it's much more likely that other planets would be seeded. Because if we want liquid water and a surface and warm, then the Earth is your best bet because it had it for the longest time. But of course, there could be rocks because Mars gets hit all the time, also with Earth's rocks. So one of the things that would be really interesting, if we ever find life on Mars, if it looks like life on the Earth, we don't know if we brought it with rovers as hitchhikers before, tiny hitchhikers that came, or maybe actually these Martians that we were to find could be Earthlings. And so what is very funny to me, and I get it, is that people kind of rather be Martians than actually us finding Earthlings on Mars that we basically seeded there.
That's
but I
funny.
think that would be the more likely scenario because Earth had more time to get life started and more diverse environments that could have given rise to life.
Yeah, I like the Paul Davies idea of a second genesis on Earth if you could find some organisms that were not based on DNA. Something like RNA or some other self-replicating mechanism that we don't use. Part of the problem is if it happened long enough ago, it would be erased, right? The rock cycle destroys everything that was, came before.
Exactly. And this is where this, tree hypothesis comes from, that we only see the survivor and what the survivor did to bloom. There could have been many starts of life, but probably the circumstances were the best for one kind of life. It could take advantage of it, and that outcompeted all the other forms of life that could have existed. But you would never know because it didn't leave life initially, it didn't leave unique signatures that are easy to spot and that are easy to distinguish, to say, oh, this was a single cellular life that has our DNA, and this is a single cellular life that has a different DNA. How do you do that? You don't have that kind of data or record. And so the idea whether or not life gets started a lot of times in a lot of different ways is a completely open idea. And I think we'll have to find life on other planets or moons or on planets around other stars to be able to actually get some insight into that question.
All right, Lisa, this is very generous of your time. We're right at 90 minutes here. Your work is so interesting. If you were talking to some, say, middle school, high school kids that said, I want to do what you're doing. What classes do I need to take? What kind of degree do I got to get? And where do I go? And that kind of thing. Give us some advice.
To me, math is a language. Think about it like you're learning Spanish. You learning a language that lets you uncover the mysteries of the universe. So, even if it's boring sometimes because that's not how it's taught, math is something that you need to underpin your search in science. And you can talk to scientists all over the world once you speak math, even if you don't speak their language, put a formula on the table and they will know what you mean. And then science, whatever speaks to you. But I think the biggest thing is try to stay curious, even if people tell you it's not cool to be curious, because there's so many things to discover out there. And if you keep going with that, if you find something that you want to know more about, whether it's planets and life in the universe, whether it's how something works, whether it's why somebody does something, stay with that, and that will lead you to your profession.
But more specifically, not just physics, but from everything you've been talking about, chemistry, inorganic and organic chemistry, probably some geology to understand how planets,
absolutely,
right? Planetary
microbiology,
microbiology
to figure out how you can grow this. And then we have a lab in civil engineering where we do the remote observation measurements. And we have a lab in the earth and planetary science where we melt these lava worlds in the lab. So there's a lot of sciences that you need to come together to figure out if there's life in the universe. So take your favorite one and choose that path. And then if we find a signal, and I hope we do, then it's not just limited to the sciences or social sciences, because then you can say, oh, how would I communicate? What would it actually mean for us? How is the psychology affected? All of this will blossom after. But first, we need to find a signal so we know where to look and what to focus on.
Nice. All right, here's the book, Alien Earths. Get it and read it. The New Science of Planet Hunting in the Cosmos. When we find living organisms elsewhere, you're coming back to tell us about what you found.
More than happy to do that.
Thank you so much.
Thanks for having me.